students, now we will see in your physics section light, the next practical, next experiment is about using a travelling microscope and finding the refractive index of glass. Not only glass, even any transparent liquid, we can find the refractive index using this travelling microscope. How are we going to find it? We studied this in theory. I am going to explain this again now here. The refractive index will be equal to the real depth divided by apparent depth. Real depth divided by apparent depth will be equal to the refractive index. We studied something like that. So first we will see what this means. What is this real depth? What is this apparent depth? How to find them? And how does that become equal to the refractive index? We will study all the theory. You have to have strong theory background before you go into the experiment. You don't understand the theory, then no point of doing the experiment. You won't be able to answer the questions that come in the experiment. You can't just memorize and go for the exams. You need to understand first of all. So first we will have a look at the theory and then the methodology, how we are going to do this, and then we will do the practical. We will do the experiment, get the readings, calculate and see whether what we are telling is truth. Right, let's have a look at the concept. Now look at these two parallel lines. Assume in between these two parallel lines, I have kept some transparent medium, meaning it can be glass, it can be water, some medium through which the light can travel. And then what I do, for the moment let's assume it's a glass block. Right. Under the glass block, I keep an object. O is an object. What could be an object? It can be a pin. On a piece of paper, I put a cross and I keep it. Some object is kept under the, so I keep the glass block like this. Under the glass block, I am going to keep an object. And what I do, I am looking at the object from here. I am looking at the object from there. So what I will see an image of the object. Why would I see the image of the object? Let's analyze the path of the rays that originates from O. The rays that come from O, how it reaches to the eye, that's what is going to show me the image. So let's see how the rays that starts from O would reach my eye. First, look at this OA. A ray that leaves from O, that starts from O, travels on path OA and reaches this surface A. I told you this is glass, this is air. So you know from one medium to another medium, when a ray travels, we have an equation, sin I over sin R equals N. From this I can say sin I equals N sin R, where N is the refractive index of the second medium with respect to the first medium, which is a constant. What is I and R? I is the angle of incidence, R is the refraction angle. We studied that in theory. We have done a lot of questions also on that. Now, how do we measure I? At the point of incidence, we draw a normal. The line of incidence and the normal, what angle they are making would be the angle of incidence. Look at this point. If I draw the normal for the surface at this point, that and the ray both are collinear because this is reaching here perpendicularly. So the normal and the incident line, incident ray have no angle between them, which means I is 0. If I is 0, you know sin I is 0. You need to know a little bit of trigonometry here. Sin 0 is 0. So the left hand side of this equation is 0, which means the other side also has to be 0. But n is not equal to 0, n is a constant which is not 0. Refractive index of one medium with respect to another medium is never 0. Right. then if this side has to be 0, obviously sin r has to be 0. Sin r has to be 0. Then only you will have equation balancing. Left hand side is 0, right hand side has to be 0, which means sin r has to be 0. Sin r 0 means how much is r? R is 0. R is also 0. R is 0 means what? The refractive ray, the refracted ray should not have an angle with the normal. Why? What is R? The refraction angle. The normal and the refracted ray, the angle between them. That also has to be 0. So what that technically means is, if the ray reaches perpendicular to the surface, it doesn't deviate, it travels in the same line, which we studied in the theory. I just recalled now the theory part of it. That's why the ray OA directly goes up and reaches the eye. So if I am looking from here, I will see the image somewhere on this line. I can't find where the depth is, where it is actually. All I would know, okay, in this line, I see the image. Where exactly it is, I don't know. Now, let's think that I'm shifting my eye a little bit to this side. That means, see, I kept the glass block. Under the block, I kept an object. I was looking like this. So I received a ray which was perpendicular to the surface. Now I'm moving a little bit. I'm moving a little bit and I'm looking like this. I moved a little bit and now I'm looking from here. So now what happens? Another ray that leaves from O and travels at path OB reaches this surface. So this is a point of incidence now. There will be a refraction because two different mediums, you know, when the light penetrates through different medium, it gets refracted. Since air is a less dense medium, it gets deviated from the normal line even further. So more deviation from the normal line and it goes like this. So if I am keeping my eye here, I would see an image on this line because the ray that I receive is BC. So I would see an image of the object and I would feel, okay, the image is somewhere on this line. That's how I would feel. So when I keep my eye here, the image is somewhere on this line. When I keep my eye here, the image is somewhere on this line. Remember, I am looking at the same image. There is only one object and one image for it. You don't get multiple images for the same object. There is one image and one object. So from both points, what I see is the same image. So that same image, that single image has to be on this line as well as it has to be on this line. Means what? It must be on the point where both lines intersect, which means this is where the image has to be. Understand? Suppose if I keep my eye from this side, again I will see a line. Right. I will feel like the line, if I keep my eye here and observe it, I will see a line, a ray coming from this point. Actually, how it happens is, a ray started from object, reaches this surface at this point, gets refracted, and it will reach my eye. But when I look through that, it will look like it comes from this image. So wherever I shift my eye, I will receive a ray that looks like coming from point I. Understand? So for me, who is looking above from this side of the glass block, I am going to feel like the image is located here. That means the object is located here. I am going to see the object at this point. I wouldn't see the original object. What I see is the image only. So for me, the object will look like it is here. This distance is what we call apparent depth. It looks like the object is there. The object will look like elevated from its real depth. What is real depth? This is going to be the real depth. Why? That's the actual depth, right? This is where the object is actually. So we call it real depth. And this gap is known as apparent depth. Apparent depth. Understand? From the top surface where the image is located, that gap is what? Apparent depth. from the top surface where the actual object is actually located, that is known as real depth. So understand first the terminology, real depth and apparent depth. This also I have taught you in the theory, just recalling the basics before we go into the experiment. Right. Then we studied another thing. From one medium to another medium. If a light ray travels, we can apply Snell's law, which gives us this equation. Right? Where what is n? From the first medium, with respect to the first medium, second medium's refractive index. With respect to the first medium, second medium's refractive index. So what I am going to find here, with respect to air, glass's refractive index is what I am going to find. Glass's refractive index is what I am going to find with respect to air. Which means for me, air has to be the first medium and glass has to be the second medium. Whereas how we are analyzing now is the other way around, right? The ray starts from air, starts from glass and it goes into air. So to reverse the situation, I have marked I here. Why I marked I here? See, if a ray starts from O, reaches B and goes through C, think about another ray that starts from C and reaching B, that has to go through the path BO. Another ray that starts from C and reaches B has to travel BO direction because it's reversible. IR can be reversed into again R and I. That means incident angle and the refraction angle can be reversed. A light ray going this way and emerging into another medium, on the same path, it can come from the other medium and come back to the original medium, first medium. That means this line is reversible. Now I have put the arrow like this. Even if the arrow is changed this direction, the path will be same. Reversible. I and R are reversible. Because of that, I mark this as I. Because I want to find the refractive index of glass with respect to air. So air has to be my first medium, glass has to be the second medium. That's why I have interchanged I and R. Understand that. So let's go with the same approach here. N equals sin I over sin R. Let's use a little bit of trigonometry here. These two lines are parallel. So if this is I, same line, this also has to be I. This also has to be I. Similarly, if this is R, this also has to be R. Why? Parallel lines intersected by same single line. So R, R, I. Understand? Let's write sin I. Sin I. Sin I. Look at this triangle, IAB triangle. Sin I has to be opposite side divided by hypotenuse. You know that. In a right angle triangle, sin theta is opposite divided by hypotenuse. This is the angle I, opposite means AB. Hypotenuse is BI. This is I, opposite, hypotenuse is BI. Similarly, sin R, if this is R, this is R. So in this triangle, sin R has to be again opposite over hypotenuse. Opposite is AB, hypotenuse is BO. Sin R. Opposite is AB, hypotenuse is BO. N equals sin I divided by sin R. Careful. If you are writing glass's refractive index with respect to air, I has to be in air and R has to be in glass. That's why I is here, R is here. Correct. Sin I is this. AB divided by BI. I have to divide by sin R. So I have to divide by this fraction. Dividing by that fraction is equal to multiplying by inverse of that fraction. Inverse means BO will go up, AB will be down. Now AB cancelled, BO and BI. BO and BI. Now understand another important part. I told you first I am looking at it vertically and I am shifting a little bit and again I am observing the image. I did not shift by a greater distance. What I shifted is a little bit, which means from this point to this point, even though I have drawn at a bigger distance here, just to make it clear to you, this distance is a negligible distance. Negligible distance. It's a small distance that I have shifted. See what happens if AB is a negligible distance. If AB becomes 0, right? Let me write it here. Look at this. If AB approaches 0, if AB becomes a smaller one, this is how we write it. AB is negligible. AB is a small distance. If that is the case, OB, the points B and A are going to align together, right? They will become the same point. So OB and OA would be same. Why? If these two are closer, OA and OB must be closer, right? There can't be a big difference between OA and OB. So I can say OB or BO and AO will be equal. Will become closer. Not exactly equal, but very close to each other because AB is a negligible distance. Similarly, IA and IB or AI and BI. AI and BI. Let's say BI will approach AI. See, this line, if B becomes closer and closer to A, this line would coincide with AI line. So BI and AI will become equal. Again, I am repeating. Here I have drawn this diagram such that AB is a bigger distance for you to look at it clearly. But in real, when you are doing this experiment, the shift that you make on your line of sight is not much. You are shifting your eye a little bit, which means A and B are very close points. The gap between them is negligible. Understand? In that case, I can say BO and AO are very close, almost equal. BI and AI are almost equal. So here I said BO over BI. So instead of BO, I can say AO, and instead of BI, I can say AI. Let me rewrite it here. So N equals, what are we getting? AO divided by AI. What is the name for AO? AO means this much. That's the real depth. Real depth. AI. What is the name we gave for AI? Apparent depth. Apparent depth. Understand? So this is the theory background of this. The refractive index of glass with respect to air will be equal to real depth divided by apparent depth. So this is the theory. This is what we are going to do in the practical. Let's see how we are going to do it. So this is what I have explained now. Let's quickly go through this. Consider an object O in the incidence medium. The light ray OB from O will get refracted at point B when it enters into another medium and will travel at path BC. OB, BC. However, the light ray OA will not deviate and will continue its path through AD in the second medium since the incident angle is 0, the perpendicular one. If DA and CB are produced to intersect at I, see DA is produced up to here, CB is produced up to here, they intersect at I, then the image of O is at I because both of them see. The refractive index of incidence medium N equals sin I over sin R, AB over BI, BO over AB, AB cancelled, we get BO over BI, I showed you this. And then I explain how comes BO becomes AO and BI becomes AI because of that real depth divided by apparent depth equal. Clear? That's the theory. Now, experiment. First, we will find the refractive index of glass. What are the materials and apparatus required? You need a travelling microscope. Travelling microscope. We will see how to use the travelling microscope. Rectangular glass block, a glass slide, and lycopodium powder. Lycopodium powder is a light yellow color powder which can be easily seen from the microscope. So, we use that powder to focus on the powder and get the images. Method. Level the microscope and make the microscope tube vertical. Microscopes, the base has to be horizontal. We have to level it first. I'll show you how to level it. And then the microscope tube can be changed. The angle of the tube can be changed. So, you have to make it vertical because we are going to measure the vertical distance. So, turn the microscope tube to be vertical. Then what you do? Place the glass slide on the base of the microscope directly under the objective of the microscope. I will show you what is objective, what is eyepiece and all that. So, after you turn the microscope tube vertically, then you bring a glass slide with lycopodium powder on that. We are going to keep the glass slide and then we are going to spread some lycopodium powder on the glass slide so that we can focus the microscope on the lycopodium powder. See, place the glass slide on the base of the microscope directly under the objective of the microscope. Spread a thin layer of lycopodium powder on the glass slide. You have to put some lycopodium powder on the glass slide. Focus the microscope to get a clear image of lycopodium powder on the cross wires and get the readings of vertical scale at this instance. Then what you do, loosen the screw for large vertical movement. There is a screw to move the microscope vertically. So, loosen that screw, move that upwards, raise the microscope and place the glass block on the lycopodium powder such that the length of the glass block is vertical. Right, I'll show you, see. This is how your glass block is. So, this is what we call length. So, keep the glass block such that this length side becomes vertical. Keep the glass block like this, right? So that you can maximize the length, maximize the thickness. Why? Going back to here, if we can maximize this thickness, right, if this T can be increased, then apparent depth, real depth both will increase. So, if the depth increases, what happens? Error will be minimized. When measuring small distances, if the error is there, the percentage error is high. Let's say you get an error of 0.1 millimeter. 0.1 millimeter error on 1 millimeter, 0.1 millimeter error on 1 centimeter, where the percentage is less. When you measure 1 centimeter, if you have 0.1 millimeter error, the percentage is less. So, always try to keep the distance or this depth bigger, T, increase the T such that in case if there is any error in the measurement, in the focus, if you are making a small error, the percentage of that error will be minimized. Because of that, it's advisable to maximize T. That's why we say whichever the longest side of the glass block has to be kept vertical. So, the T is maximized. That's the point we are mentioning here. Loosen the screw, raise the microscope and place the glass block on the lycopodium powder such that the length of the glass block is vertical because we are trying to maximize the T. Again, focus the microscope on the powder and get the reading. So, next time when you are focusing, see there was powder, on top of powder you have kept the glass. Now, when you are focusing, you are actually focusing on the image. You are going to focus on the image. Now, spread some lycopodium powder on the glass block, focus the microscope on it and get the readings. So, I will show you. Right, we are going to get 3 readings now. First, what we do, and you keep some powder and you are focusing on it. So, that's the reading number 1. This is where we are going to get reading number 1. Then what you do, there was the powder, you have kept the glass block. You have kept the glass block. So once you have kept the glass block, what will happen? You will see the image of it. Where would be the image? The image would be somewhere here. So this is the second reading. That's the second reading. We are focusing on the image. After we keep the glass block, see, this is where the lycopodium powder is. And you have kept the glass block. When you observe from here, we already saw in the theory, you will see the image elevated from the actual point. So image is going to be here. For this point only you are focusing now. So this is where you are getting the second reading. Second reading. Third reading, what you do? You had the slide and you kept the glass block on that. And now you put the glass powder, the lycopodium powder on top of the glass block. On top of the glass block. Now when you observe, you are going to get this point's reading R3. R3. Right? So, see, without the glass, focus on the lycopodium, R1. You keep the glass, the image of this lycopodium you will get here, R2. Then on top of the glass block, you put the lycopodium powder, get R3. R1, R2, R3. So from R1, R2, R3, how do we get the real depth and apparent depth? I'll show. Let me put all of them in the same diagram. Look at this. This is my glass block. This is where the original reading was taken, R1. Then the image is here. This is object, this is image. For this image, you are getting R2. And then you keep the lycopodium powder on top of the glass block and get R3. R1, R2, R3. So if you want to get the real depth, that is R3 and R1 difference, right? This is what the real depth is. I have explained that in the theory. So real depth has to be R3, R1 difference. R3, R1 difference. Right? R3, R1 difference. Apparent depth. What is apparent depth? Where the image is. This gap. Which means R3, R2. Third reading, second reading difference is going to be the apparent depth. And we studied N equals real depth divided by apparent depth, which means R3 minus R1 divided by R3 minus R2 should give us the N, refractive index of glass. Understand? So this is what the practical concept and steps are. Right? So now what we are going to do, let's do this practical, let's do this experiment, let's get the readings R3, R1, R2 and then see whether we are getting the refractive index. Dear students, now we are going to see the second practical in light, where we are going to find the refractive index of a glass block using the real depth, apparent depth approach. We can use this approach to find the refractive index of a glass block as well as any other liquid also. So first we will see what instruments or what apparatus are required to do this practical. So the apparatus required, the first one, the main one in this practical is this traveling microscope. In measuring equipments, I have told you how to use this traveling microscope, how to get the reading and all, we have explained clearly. So in this practical, we will not be explaining too much as to how to use this. But this is the main instrument in this experiment. Using this only, we are going to measure the real depth, apparent depth, everything. Then this is the glass block. It has to be a rectangular glass block to measure the real depth and apparent depth of it to find the refractive index of the glass. And then we need lycopodium powder. We use the lycopodium powder to focus on the microscope and measure the depth. We need a small strip of glass. On this glass strip only, we will be spreading this lycopodium powder and we will be observing that through the microscope. If you don't have the glass strip, then you will have to spread the lycopodium powder on the microscope itself. To avoid that, we use a glass strip. And we need a magnifying glass to get the readings clearly. We have a vernier like reading scale here. So you need a magnifying glass to get the readings clearly. In some of the traveling microscopes, you will have a leveling bubble. Here I am using a separate bubble level or spirit level to measure the horizontal level to ensure that the microscope is in horizontal level. Before we start the practical, we have to ensure that the microscope is kept on a horizontal plane. To ensure that, we will be using this bubble level. As I mentioned previously, let's use this bubble level to ensure that traveling microscope is horizontally leveled. So you can see the bubble is right in the middle in between the two lines, which ensures that it is on a horizontal plane. If it is not in a horizontal plane, if you don't see this bubble right in the middle here, you can adjust these screws. You have two screws. You can adjust them to make it horizontal and bring this bubble to the middle. That's how we adjust the horizontal plane of this microscope. Once that is set to be horizontal, so after you have set the horizontal level, now let's be familiar with more parts of this instrument. This piece is what you call eyepiece, which means through this eyepiece only you are going to observe the object. So where would you keep the object? Always the object has to be kept on this end of this instrument. Sometimes when you go to the lab, see, you may have this in a different angle. You might have it like this. So you must know how to adjust it, which piece or which side of it you are going to keep it to your eye, in which side of it you are going to keep the object. Be familiar with that. The side where you have the lens, is the eyepiece. And the other end is where you are going to keep the object. So you can adjust it. If you want to get the reading of an object in front of this meter, in front of this microscope, you can set the eyepiece like this and you can tighten it. But in this practical, we are going to keep the lycopodium powder here. So we will have to observe it vertically. Therefore, we will adjust it. We will keep it vertically and fix it here. That's the first thing you have to be familiar with this. And there are a few other parts of this instrument which will help you in fine-tuning the focus. So I'll tell you step by step how you are going to fine-tune and focus to the object. First thing, be familiar with this screw. You have a screw here. Once you loosen this screw, you can adjust this up and down by a greater extent in centimeters, right? So once you keep the glass block, if you want to raise this by a few centimeters, you can always loosen this screw and then adjust it. After you adjust it, you may not be able to get a fine tuning, but you might bring it to a closer point and then tighten it. Make sure you tighten it after you have adjusted. To get the fine tuning after that, you have another screw on the top. This is also for fine tuning. So by greater extent, if you want to raise it by centimeters, you can always use this screw. But if you want to raise by millimeters or part of millimeters, if you want to do the final fine tuning, you can always use this screw. In the meantime, you must understand, here you also have another screw to focus and fine tune your object. But one thing you must understand, at the beginning you can use this screw. When you get the second reading, third reading in this practical, that means after you keep the glass block, when you try to get the second reading, you will not adjust this one. Because when you adjust this screw, the vernier scale doesn't change. So by adjusting this, if you will get a new reading, that will not be reflected on your vernier reading. So since we are measuring the real depth and apparent depth, every adjustment we do, we want to see it in the vernier scale. So after you have used it first time in this practical, when we get the second reading, third reading, make sure you don't adjust this. Whatever the adjustment vertically you want to do, you can loosen this screw and adjust the height of it. If not, you can use this fine tuning screw. Apart from that, you have another horizontal vernier scale here. You can adjust that by this screw. That is for if you want to get any horizontal readings. If you want to measure the width of something, then you can use this. But in this practical, we are not measuring anything horizontally. We are measuring the vertical depth, the real depth and the apparent depth. We are measuring vertically. Therefore, we will not be using this vernier scale in this practical. But one thing you must understand, when you are using this vernier scale, you have a screw here. This screw has to be tightened. If this screw is loosened, then when you adjust this screw, the microscope will not be traveling, it will not be moving. Right? Once you loosen this screw, you can manually adjust it. You can manually adjust it. After tightening the screw, then only you can adjust it with this screw. Right? So if you want to adjust this horizontally by a bigger scale, like in centimeters, then you can loosen this screw, and then manually you can adjust it. See, you can manually adjust it. Then you tighten it to get a fine tuning, you can use this screw. But again, I am repeating, in this practical, we are not moving this microscope horizontally. Therefore, these screws and this vernier scale will not be used in this practical. Now let's take the glass strip and spread the lycopodium powder on this. There is one thing you have to note when you are spreading lycopodium powder on this. Make sure the powder is in a very thin layer. If the thickness of the layer is significant, when you measure the real depth and apparent depth, that will have an impact. So make sure you spread the lycopodium powder in a very thin layer. Right. Now that is a thin layer of lycopodium powder on the glass strip. Let's keep it right under the object piece of this microscope. Now since this is the first time I am going to read in this experiment, I can use this screw to adjust and find the best focus to get the reading. But first time I can do this, not for the second reading, third reading. I told you the reason, because when you are adjusting this one, the vernier scale doesn't move. So after you get the first focus, for the second focus, we need to know by how much the lens or the microscope has moved. That we have to measure on the vernier scale. So first reading, it is okay to adjust this and get the reading, but not for the second or third readings. Now we can observe the lycopodium powder through the eyepiece and adjust the focus. You can see the crosswire. Adjust the focus until you see the lycopodium powder clearly. So now you can see, we can focus on the lycopodium powder. It's becoming more clearer. Once you get the best image of it, once you have fine-tuned it, then we have to get the reading. One more thing I have to tell you at this point. When you keep this traveling microscope, you must always keep the vernier side towards you. Otherwise, after you fine-tuned to get the reading, if you have kept it on the other side, then you have to go to the other side and get the reading. So make sure when you keep the microscope, the vernier is always in your side. Now let's get the reading. Let's get the reading now. So first we have to get the main scales reading. It's above 2. And then above 2, I have to find out where this arrow is. So that is at 2.1, 2, 3, 4, 5. That means 2.45. In millimeters, that will be 24.5 millimeters. 24.5 millimeter is the main scales reading. After I get the main scales reading, I have to get the vernier reading. So I need to see where this vernier line is aligned with the scale in the main one. So you can see that here at 0.35, you can see 0.35, the lines are aligned. So the vernier reading, we are getting 0.35 millimeter. So we got the main reading 24.5 millimeter and the vernier reading we got 0.35. So the reading is 24.85 millimeter. Now let's write this on our table. So the first reading we have got 24.85 millimeter. Now let's keep the glass block and get the reading after keeping the glass block. So now what we do, we are going to keep the glass block on top of this lycopodium powder. So you know when we keep the glass block on the lycopodium powder, you can see the image of lycopodium powder. That will be a little bit above where it is actually. So I am going to observe that from the microscope. So now there is one thing you have to understand here, in which orientation I should keep this glass block. I can keep it like this itself, but the thickness in this orientation is less. So what will happen, by the distance it gets shifted up, the image by how much it gets shifted up will be a small measurement if I use this thickness. So that will bring a higher percentage of error. In order to minimize the error, I should keep the glass block such that the thickness is maximized. So one option I have, I can keep it like this, so that this entire length becomes the thickness. But the problem with that, stabilizing this in this orientation can be a bit difficult. Therefore, what I'm going to do here, let's keep the glass block in this orientation, so that I have sufficient depth here and I can comfortably stabilize this also. So now on the lycopodium powder, I'm going to keep the glass block in this orientation and get the measurement. For that, I will have to adjust the microscope to get sufficient space. Now, let me adjust it in the main scale to bring it closer to the focus point, and then we can fine tune with this vertical fine tuning screw. When I get almost a good image of the lycopodium powder, I'll fix it here, and then let's adjust it with the vertically fine tuning screw. Now you can see I'm getting a clearer image of the lycopodium powder. Once you get the best image of it, you can stop adjusting it and get the reading. Remember what I mentioned previously? Now when you are getting the second reading, you should not adjust this screw, because if you adjust on this, it will not vary on the vernier. But the lens will get adjusted, we will not get a reading here. So make sure when you get this second reading after keeping the glass block, you should not adjust this screw. You must adjust only with this one. If you want to increase by a bigger scale, you can adjust with this one, and for fine tuning, this screw only, vertically fine tuning screw. Now we have got the best image of it. Let's get the reading. So you can see in the main reading, I have to see where this arrow is. So in the main reading, 4.5, 4.6 it has passed, but not 4.65. So I can get the main scale reading as 4.6, that is centimeters. So in millimeters, 46 millimeters. Then I have to see in the vernier where the line of a vernier is aligned with another scale in the main scale. Around here you can see 0.46 You can see 0.46 is aligned. So in the vernier reading, it will be 0.46 millimeter. In the main reading, I got 46 millimeter. In the vernier, 0.46 millimeter. So the final reading will be 46.46 millimeters. So the second reading we are getting, that means after keeping the glass block on top of the lycopodium powder, the reading we have got is 46.46 millimeter. You know, we have to take another reading as well, where we have to keep the lycopodium powder on top of the glass block and get the reading. So before that, let's write this in our table. R2 is 46.46 millimeters. So let's write down the reading for R2. We got 46.46 millimeter. 46.46 millimeter. Next we have to do the third reading, where we keep the glass block. On top of the glass block, we will keep the lycopodium powder and get the reading. We have to put the layer of lycopodium powder on top of the glass block. I'm going to keep it here and get the reading. But make sure you keep this strip of glass also under that, because we kept this glass strip in the previous readings as well. So to get the reading this time also, I have to keep the glass strip underneath. Otherwise, it will be an error in the practical if you don't keep the glass strip here. Now, let's check the image of this lycopodium powder through the lens. I don't see a clear image of this. Let's adjust it on the main scale first. Until I see somewhat clear image, I won't be able to get the fine-tuned image with this scale. Now, let's adjust the vertical fine-tuning screw and get a clearer image. Now you can see it's becoming more clearer. Get the best image you can. Now let's get the reading on the vernier. Right, now we'll get the reading. See, the line is just above 89.5 millimeters. See, 89.5. It has crossed the 89.5 mark also. So in the main scale, what we are getting is 89.5 millimeter reading. Then we'll see which line of vernier is aligned with another line in the main scale. You can see somewhere around here 0.1 millimeter. That is where it is aligned. So vernier reading is 0.1 millimeter. Main scale reading is 89.5. Altogether 89.6 millimeter is the third reading that we are getting here. So we have got the third reading now, 89.6 millimeter. Let's record this also in our table. So you know, I have to get the difference between third reading and first reading. That will be the real depth. Third reading and second reading difference will be the apparent depth. The ratio between real depth and apparent depth will give the refractive index of the glass block. So now let's write R3 and do the calculation. The reading for R3 we have got is 89.60 millimeters. We have got all three readings, R1, R2, R3, we have got all three readings. Now we can find the real depth, apparent depth and find the refractive index of this glass block. Now, see, these are the readings we have got. R1, R2, R3 in millimeters, we have got these readings. R1 is 24.85, R2 is 46.46 millimeter, R3 is 89.6. R3 minus R1, you have to subtract this, right? So that will be 89.6 minus 24.85. If it is 25, we will have 64.75. Similarly, R3 minus R2, you will have 46, 89, 43.14. 43.14. So R3 minus R1 is 64.75 divided by 43.14. And the answer you are getting for this, right, you can divide and see 1.5009, say 501 is what you are getting, 1.501, right? So that is what the refractive index of glass we are getting. Now understand, we can do this practical for any transparent liquid also. So we will repeat this practical for water and see what refractive index we are getting for water. So the refractive index of water, to find that using travelling microscope, what are the materials and apparatus required? You need the travelling microscope, a small beaker, right? You need a small beaker, not a lengthy one, a beaker which can be kept under the microscope tube. So a small beaker and some water, optical pin, lycopodium powder. Method. Look at the methodology. You must be able to write this methodology for the exam. Place the small beaker under the microscope and drop an optical pin in it. That means you take the beaker, keep it under the microscope tube, directly under that, on the base of the microscope, travelling microscope, you keep the beaker and drop a pin inside that. So pin is what the object is going to be. So we will be focusing the microscope on the pin. See, focus the microscope on the pin and get the readings. Right? See, this is how your microscope is going to be. You kept the beaker. Here you have put a pin in the bottom. And focus on this pin and get the readings. That will be reading number 1. That will be reading number 1. Then what we do? Fill the beaker with water up to approximately 20 millimeter height. It doesn't have to be exactly 20 millimeter. Usually 2 centimeter, 3 centimeter, 4 centimeter. Those are the levels of water we use. Actually having more height is better. But remember, this practical is usually used for materials or the liquid that is scarcely available. Like water, you can find any amount usually. But there are some other liquids which are not freely available, which are not available in large quantities, which are rarely or which are scarcely available. So those materials, those liquids, you won't get a lot of liquid. Then you have to use as minimum as possible to do this practical. So you need to keep at least 2 centimeter height. Don't go lower than 2 centimeter because the errors will be high. So keep at least 2 centimeter height and do this practical. Right. Again, focus the microscope on the pin and get the readings. See what happens now. This was your beaker. You kept a pin. Then what did you do? You filled it with water. Microscope is here. So when you look through the microscope, what happens? We will see the image of it. Let's say the image will be somewhere here. I already explained. The image you see will be elevated from where the actual object is. Now focus to see the image of this. You will see only the image. Even though it looks like the object, what you see is the image. At this point, you get the second reading, R2. That's what this is about. Again, focus the microscope on the pin and get the readings. Spill some lycopodium powder on top of the water surface. Now after that, what do you do? Now the pin is here. You fill some water. You already filled water. On top of that water, you are going to put some lycopodium powder. So you are going to put some lycopodium powder somewhere here. And your microscope is here. Now what do you do? Focus on this one. Focus on the lycopodium powder and get the reading. Reading number 3. Right? Focus on, now focus the microscope on the lycopodium powder and get the readings. Using the above readings, calculate the real depth and apparent depth. So see, if I bring all the readings into one diagram, this is how the beaker, we have the pin here, image here, water, lycopodium powder here. So at this point you got reading 1, reading 2, reading 3. Am I right? Reading 1 was without the water, only the pin was there. You focused on the pin and got the reading. That is reading number 1. Reading number 2, after you filled that with water, again you focused on the pin. That means you will be seeing this image. So that is reading number 2. You are focusing at this point, reading number 2. Then what you do, you spread some lycopodium powder on top of this surface. Focus on those lycopodium powders and get the reading. That will be reading number 3. Now, if you get the difference between these two, R3 minus R2, that will be the apparent depth. Apparent depth. The difference between R3 and R1, the difference between these two has to be the actual depth, the real depth. So, you have got the apparent depth, you have got the real depth. You can find the refractive index. So, this is what we are going to do for the water. Not only water, any other transparent liquid through which the light can travel, we can do this experiment. This is particularly useful when the availability of the liquid is limited. If you don't have the liquid in abundance, if you don't have the liquid in large quantities, this method of finding the refractive index is considered to be one good method, right? Because you just need the liquid to fill the beaker up to 2 centimeter, at least up to 2 centimeter. So that will be few milliliters of liquid that you need, right? So now let's see how we are going to do this practical. Now students, we can use the same approach to find the refractive index of any transparent liquid. See, we are using similar apparatus again, the travelling microscope, a beaker, you need a pin and a hand lens or magnifying lens to get the vernier readings. Again, we will be getting 3 readings in this experiment like we did with the glass block. First, what you do, you drop the pin inside the beaker, keep it under the lens and get the reading, point number 1. Second, fill this with some water, keep the pin under the water or inside the water and get the reading, reading number 2. Finally, on top of the water, spread some lycopodium powder and get the reading, reading number 3. The difference between third reading and first reading will be the real depth of water. The difference between third reading and second reading will be the apparent depth of the water. You get the ratio between real depth and apparent depth. That will give you the refractive index of water. You can do this experiment not only to water, any transparent liquid, you can do this practical. Let's try that with water and find the refractive index of water. So as the first step, let's drop this pin inside the beaker, keep it under the lens, and through the eyepiece, let me check and focus the lens. Once I get a clear image of the pin on the crosswire, I have to get the reading. Let's check the image of it now. I don't see any image of the pin. So let me adjust it on the main scale. I can see a blurred image. Now let's fix this and adjust with the vertically fine-tuning screw. Now you can see a clearer image of the pin. At this position, I have to get the reading of the vernier. In the main scale, you can see the arrow has just passed 62.5 millimeter in the main scale. And in the vernier, you have to see where a line is aligned with another scale with the main one. It's around 0.15 millimeter. You can see 0.15 millimeter in the vernier. So the reading we are getting 62.5 in the main, 0.15 in the vernier, altogether 62.65 millimeter. The first reading we have got is 62.65 millimeter. Now students, to get the second reading, what we have to do? We have to fill some water in this beaker. Having the pin inside the beaker, we have to fill it with some water. Usually 2 centimeter or 4 centimeter is the usual height of water that we fill to do this experiment. So let me fill it up to 2 centimeters. Approximately 2 centimeter is the height of water. Now you know, when I look from the top, I can see the image of the pin. The image of the pin will be elevated from its actual position because of the refraction of the light rays. So I have to adjust my lens to get a clear image of this pin. Let me check that. As I mentioned, I don't see a clear image now. Let's adjust it vertically. Let's fine tune it with the vertically fine tuning screw. Now you all can see a clearer image of the pin. Once you get a clearer image of the pin, let's get the reading of vertical scale we have here. So you can see here, I need to find the main scale reading just below this arrow. So here you can see in the main scale, we have passed 6.5, that is in centimeters, 65, 66, 67.5. The arrow is just above 67.5 millimeter. Then in the vernier, I have to see which line becomes collinear with another line in the main scale. That means the two lines have to be aligned. So you can see here 0.1. 0.1 means 10 sections of vernier scale. 0.2 means 20 sections of vernier scales. So here in 0.2, that is 20th section of vernier aligns with the main scale. Can you see that, students? That means 20 scales of vernier. 20 scales means that is 0.2 millimeter. You know, in vernier, one scale is 0.01 millimeter. So 20 small scales means it's 0.2 millimeter. You don't have to count it, it is marked there, 0.2 millimeter. So in the main scale, we got 67.5. And in the vernier, we got 0.2. So the final reading is 67.7 millimeter. That will be our R2 reading. So now let's write down the reading R2, 67.7 millimeters. Let's write it down on our table. Let's write down the second reading we have got, 67.70. 67.70 millimeter is the second reading we have got. You can see here I have put some lycopodium powder on top of the water. So I'll keep this water with lycopodium powder under the lens. Let's focus and find the depth of this water. Let me check this through the eyepiece. I don't see a clear image. Let's adjust the height. Now let's fine tune with vertically fine tuning screw. Now you can see a clear image of the lycopodium powder. Right. At this point, I can get the reading on the vertical scale. Now you can see here, I have to get the reading on the main scale just below the arrow in the vernier. You remember first reading we got when the main scale was around 6 centimeter. Now it has come to 8 centimeter and above. So approximately 2 centimeter difference is there approximately. This will give us the height of water or depth of water that we have used. So we'll get the accurate reading. You can see the arrow is just above 8.4. 8.4 is centimeters. That means in millimeters, it will be 84 millimeter. 84 millimeter is the reading I am getting on the main scale. Then need to see which line of primary scale is collinear with another scale in the main scale. So you can see here 0.15, that means 15th section of vernier scale becomes collinear with another scale in the main scale. You know each subsection in vernier is 0.01 millimeter. So 15 subsection means that must be 0.15 millimeters. Check that, students, again. The 15th subsection is collinear, that is 0.15 millimeter. So the reading in vernier is 0.15 millimeter. So the final reading here will be 84 in the main scale, 0.15 in the vernier, altogether 84.15 millimeter is reading 3 that we are getting here. So the third reading we have got is 84.15 millimeter. Let's write it here, 84.15 millimeter. Now we have got all 3 readings. You know R3 minus R1, the third reading minus first reading will give the real depth of water. Third reading minus second reading, R3 minus R2 will give you the apparent depth. The ratio between real depth and apparent depth should give us the refractive index of water. Now let's calculate that and see what value we are getting for refractive index of water. So with water, the readings we have got R1 62.65, R2 67.70, R3 84.15 millimeters. We need to get R3 minus R1 to get the real depth. R3 minus R1, 84.15 minus 62.65 will be 21.50. 21.50 millimeters. In centimeters, you can say 2.15 centimeter. R3 minus R2, 84.15 minus 67.70, 16.45. 16.45, right? If it is 68, you get 16, and 70, 115, 45. Yeah, 16.45 millimeter is the apparent depth you are getting. We'll use it here. R3 minus R1, 21.50, 16.45. If you divide it, the answer you are getting for this is 1.307. In 3 decimals, 1.307. That's the refractive index of water we are getting from this experiment. Right? You know, refractive index of water has to be 4 by 3. That's what we study in theory. That's 1.33. We are getting 1.307, very close to the actual value. Understand? So this is how we use the traveling microscope to get the refractive index. How did we find that? With the concept called real depth, apparent depth approach. Understood? Right. So practice this, study all this theory. Now we will see how to do questions that have come in the past paper, and in the future what type of questions can be tested on this practical, we will see how. Alright students, now let's see whatever the past paper questions that has come with relevance to this experiment that we have done. Look at this one. This is an old one, 1992. In a cylindrical shaped container with height h, a transparent liquid with refractive index n has been filled to a height of h. As shown in the diagram, a pin P1 has been dropped under the liquid. A mirror, another pin P2, a meter ruler and sufficient amount of liquid are given to you. Actually, this is another practical that was there in the syllabus previously, but now they don't have it in the syllabus, but still, you know, questions can be tested on this. You can get essay questions or MCQ questions on this, right? It is not as an experiment in your syllabus, but still questions can be tested on this. So what happens here, on a beaker, you have filled some liquid. It has to be transparent liquid. And you drop a pin to the bottom of this container. Then what do? We use a mirror and a pin. Mirror and a pin. How we use that? Look at this. You will fix the mirror here, right? Right at the top of the container, you fix the mirror. This is how the mirror will be. Then above the mirror, you fix a pin. That's a pin, right? I'll put an arrow here to say it's a pin. I'll put an arrow here to say it's a pin. Fix them on a vertical stand. Fix them here. So now what happens? The image of this pin, you can see through this mirror. On the other side, when you look into the water, you can see the image of this pin as well. An elevated image. If the pin is here, if this is the real depth, you know, real depth, apparent depth. Apparent depth is less than the real depth. That means the image of the pin you will see a bit more elevated than where it is. So P1's image you might see, let's say you see somewhere here. Let's say it's P1's image. Let me mark it as P1 dash. Then what you do, this is P2, right? Adjust P2 up and down until you get P2's image coinciding with P1's image. That means P2's image also has to come at the same point. P2 dashed. Understand? So P2 has to be adjusted. You can take it up, take it down. You know, you can adjust P2 until you get P2's image coinciding with P1's image. So how do you look? You have to look through this mirror. At the same time, you have to look through this as well. So maybe one eye through the mirror, one eye directly into the water. So when you, the eye that looks directly into the water will see this image. The eye that looks into the mirror will see the image of P2. So P1's image, P2's image, both have to be aligned. If you shift your eye a little bit back and forward, you must see the images moving together until you come to a position like that. P2 will be adjusted. P2 will be vertically adjusted. Clear? Right. Then, so they are asking in the given diagram, show how you would fix the mirror and pin P2 in order to find the position of pin P1's image. So this is how you fix it. P2 must be movable. You must be able to move it. The mirror will be fixed. But the P2, the pin has to be movable because you move this up and down until the images coincide. Then, briefly explain the method to find the position of pin P1's image. That's what I told you now. What do? Fix the image or fix the mirror on top of fix the mirror on top of the container or beaker, look vertically from the top, through the mirror and into the water. You have to do that simultaneously. While you are looking into the mirror, at the same time you have to look into the water as well. So the image in mirror, image in water, you must be able to see both. Simultaneously you are doing this. Move P2 up and down until P2's image coincides with P1's image. Right. Basically, when you move your eye, there shouldn't be relative motion between P1's image and P2's image. So at this point, you have located P1's image. Right? At this point, you have located P1's image. At this point, P1's image is located or it's found. When the position of P1's image is found without an error, that means you have done this part without error, the distance of pin P2 from the mirror is measured as A. Express the distance V measured from the liquid surface to pin P2's image in terms of A, H and H. Let me redraw that for you. See. Right. You have put water up to here. This is water. Here we kept the mirror. This is the mirror. Then you kept a pin here. Pin. You already had a pin here. So this is P1. This is P2. P1's image will be somewhere here. Right? This will be P1's image as well as P2's image. Why? You have, coincided both images. Now, what do they mean by V and what do they mean by A? The distance of pin P2 from the mirror. This distance is A. They have given this distance as A. So, if this is A, understand, think about the mirror P2 and P2's image. The object distance and the image distance have to be equal. Where is the image of P2 on this line? So, mirror to this line, again, this distance has to be, again, A. Why? Object distance and the image distance have to be the same. Already we have marked this to be capital H. And this is H. Right. And they say, express the distance V measured from the liquid surface to pin P2's image. So, what they mean by V is here. This is V. So, they are asking you to find V in terms of others, A, H and H, capital H and simple H. It's easy, look at this. This is my plan. From A, if I can subtract this much, see, if I can subtract this much from A, if I can subtract that much, that should give me V, right? So, how much is this? Capital H minus small h. So, answer for this one has to be from A, if I subtract capital H minus small h, that should give me V. V is what? From the surface, from the liquid surface to pin P2's image, the distance. Pin P2's image is here. That is where P1's image is also from the liquid surface to image. Whatever the distance we have is what we marked as V. It's very easy. Look at this. This much is A. From A, you subtract this much. How much is that? Capital H minus simple h. So, A minus capital H minus simple h. Write down the expression for liquids refractive index. Now you understand, forget about P2 now. This is the point where P1 is also, right? Which means for P1's image, I know the real depth and apparent depth. Real depth means simple h. That means from the water surface or the liquid surface to the pin where actually the pin is, the depth is simple h. From the liquid surface, the depth up to P1's image, this is where the P1's image is, that is V. So let me say V is apparent depth. Apparent depth. This is V, right? H is real depth. We know N equals real depth divided by apparent depth. Real depth divided by apparent depth. Real depth is H. Apparent depth is V. V is what? A minus H minus H. This is what is N. So N equals H divided by A minus capital H minus simple h. Right? The next one. If we have to find the value of N using a suitable graph, what is the useful variable parameter that can be measured easily? Now look at this. This is what we have written here. N equals H divided by A minus H minus H. I need to find N using a graph. That means I'm going to change some values and then against those values I'm going to draw a graph. Now let's analyze A, H and H. A, H and H. Capital H is fixed. That never changes. Capital H is fixed, right? That never changes. So I can't take that as a variable because that is fixed. That is fixed, right? So all what I can measure, A and H. To draw any graph, you need two variables, right? A and H is what I can measure. So that means what we can do here, we can adjust the position of P2, or we can change H. That means change the amount of water you have in the beaker, right? Change H. So obviously when you put more water, now the position of the image is going to change. That means the apparent depth will change. So to align P2 and P1's images, you will have to adjust P2's position. The mirror's position doesn't change. On top of the beaker, you have fixed it. So mirror is fixed. On top of that, if P2 changes, A will change accordingly. So what will change here? You will change H. H is what? The depth of water. Depth of water has to be changed. Then when depth of water changed, accordingly, every time you will change A. So what are the variables I can take here? One is the depth of water. Water or liquid. They didn't say water. They said some transparent liquid. So let's also call it liquid. The depth of liquid. Liquid in beaker. The other one, the distance of P2 from the mirror. From the mirror. We can say A, H. Understand? If you want to find N, N is a constant. Capital H is also a constant. So obviously other two have to be the variables. Right? You don't have to think too much here. Now, assuming the parameter D in D is measurable independently, rewrite the formula in C for drawing the graph. N equals H divided by A minus H minus H is what we have here. You know, usually for the graphs, we need to bring it into Y equals mx plus C format. Y equals mx plus C format. And you know, H and A are the variables. So Y has to be A, X has to be H. Why? H is the independent variable. H is the independent variable. So we'll take X as H and Y as A.
cross multiply n a minus h minus h is h. Right, I want to keep a here. So we'll take n to the other side, a minus h minus minus plus h, 1 over n h. A equals, bring this h to the other side, you will get 1 over n minus 1 h plus capital H. There you go. Y, all this is going to be m because that's a constant. The refractive index of the liquid is a constant. So this bracket will be constant. H is something that we are going to change. And this is also a constant. Y equals mx plus c. Clear? So this is the formula applicable to draw the graph. Next. The graph drawn for C above has a gradient of minus 1 by 4 and intercept of 50 centimeter. Find the liquid's N and the height of container H. Once you have got the graph, format M, gradient is 1 by N minus 1. Gradient 1 over N minus 1. That is what they have given as minus 1 by 4. So 1 over N will be, take this 1 to the other side, 3 by 4, N equals 4 by 3, 1.33, N equals 1.33. Also they are asking you to find the height of the container, H. Straight away you can say intercept. Intercept is capital H, which means intercept is H. That is what we have got, 50 centimeter. Clear? So gradient gives us, from the gradient you can find the refractive index. Refractive index is 1.33 and intercept is giving you the height of the beaker, height of the container, that is 50 centimeter. Right. So that's all from that question, 1992 A level. As I told you, that's actually an experiment which we don't do as a separate experiment in the theory now, but still it can be tested because the concept is still applicable. It can be tested. So have an understanding about how that experiment works. Now we will see another recent question, 2018 A level, a question on the same thing. Let's see. You are asked to find the refractive index of glass using a rectangular block of glass and a traveling microscope. A small amount of lycopodium powder and a piece of white paper cut to the size of the glass block are also provided. A letter X is marked in the middle of the white paper. Diagram of a traveling microscope that can be used in this experiment is shown in the figure. So this is the traveling microscope that we used in our experiment. You all saw that. You all saw how we, used that for our experiment. Right. Now we'll see what are the questions they have. First part. Identify the parts marked by A, B, C, D and briefly state their functions. So you all can see here, A refers to the knob here. What do we do with this knob? This is the vertically fine-tuning knob. We call it vertically fine-tuning knob. So let's give the name for that. Vertically fine-tuning knob. You can say knob or you can say screw, right? Vertically fine-tuning knob or screw. What is the function of that? This is used for fine-tuning. Vertically, if you want to shift it by a larger distance, you don't use this A. What do? You loosen this H and then lift it up. You can lift it manually up and down. You can loosen this H, right? You can loosen this H and you can lift it up and down manually if you want to move it by a larger distance. But if you want to get the fine-tuning, when you got the approximate, image, still you want to get a clearer image of that, you do the fine-tuning with this knob. So let's say the function of this is to fine-tune the microscope vertically to get a clearer image. To get a clearer image, right? To see the most clearer image, what you do? You do fine tuning. You had used the term fine tuning. If you did not use the term fine tuning, no marks for that. Next one, B. B is this one. What do we do with B? B is to adjust the tube of microscope, right? You can move the tube up and down with that. But remember, once you move that, that will not be reflected on the vernier scale. You remember that, right? So let's say the knob to move the microscope tube. Knob to move the tube or microscope tube. What is the function of that? To move the tube, microscope tube, up or down. You can loosen that or you can tighten that by rotating that. You can move the tube, microscope tube. This tube only will go up and down, not the entire microscope system. Only the tube will move up and down. C, where is C? C is these screws. You know what we do with those screws? What do we do? Horizontally, leveling screws. Let's say leveling screws or leveling knobs. What do we do with them? By adjusting these screws, the base will be set horizontal. The base will be set horizontal. By adjusting those screws, we can make them horizontal. D, where is D? D refers to this one. What is D? D is the bubble level. When we did the practical, we used a separate bubble level and I showed you, how to get it horizontal. But we have a bubble level on the microscope also. See this one, D. So that is the bubble level already there in the microscope. So we'll call it bubble level. Bubble level, or you can say spirit level. To check whether the base of the microscope is horizontal. To check whether the base of the microscope is horizontal. So you look at that bubble and adjust these screws marked by C. Adjust those screws to make it horizontal, right? So anybody who has gone through, who has done this experiment, who has seen what I was doing with this experiment, would know all of them, because I have used all those knobs, I have used all those screws in calibrating and adjusting this instrument. So if you were watching when I was doing this, you wouldn't have any problem finding the names and functions of each of those knobs. Before starting the experiment, while familiarizing with the traveling microscope, a student observed that when the fine adjustment knob relevant to the horizontal movement was turned, the corresponding vernier scale did not move. Give the reason for this. So there is a like we have for the vertical fine tuning or fine adjustment knob, for horizontal also we have a knob. But what this says is, when you rotated that, it did not move. So you know why it doesn't move like that. There is another screw to lock that. That means when you want to move it freely, you have to rotate, you have to loosen a screw and then move it freely. After you moved it freely, you lock that screw. If you lock that screw only, then the fine tuning screw will work. If you did not lock that screw, fine-tuning screw will not work. So that's the reason you rotated the fine-tuning screw, still you didn't see any movement because you did not lock the other screw. What's the name for the other screw they have here in the diagram? See F. F. This is that screw. F is the screw. You loosen that and move it freely. Then once you have come to the approximate position, tighten it, lock it, and then adjust with the fine-tuning. If you did not lock that screw, in this case F, so it's easy to say screw F. Let's call it screw F. The reason screw F was not locked or not tightened. Right? If you did not tighten that screw, then the fine-tuning wouldn't work. That's the same case for the vertical one also. But people won't miss to tighten that. Do you know why? If you don't tighten that, the vertical one also, you have a screw, you can rotate it, you can loosen it, move it, fix it, then you do the fine-tuning. But if you don't tighten this, fine-tuning won't work. But nobody will miss it. Do you know why? If you don't tighten that, the microscope will fall down. It doesn't remain where you wanted it to remain. So everyone, the vertical movement screws, the large scale vertical movement screw, nobody will miss it. They will fix it because they know if they don't fix it, it will fall down. But horizontal one, the large scale horizontal movement knob, even if you don't tighten it, it won't make an impact. You will realize only when horizontal fine-tuning knob is rotated, it won't move. The reason is not that it has a malfunctioning, not that it has a problem with the instrument. It is because you did not tighten that large scale horizontal movement knob. So rather than writing that large scale horizontal movement knob, you can simply say F because they have named it F. If you couldn't find it, you write it in full. The large scale horizontal movement screw was not tightened. Next. An enlarged figure of the main scale and the vernier scale of travelling microscope are shown. Calculate the least count of this travelling microscope in centimeters. Least count. Let's see. The vernier has 50 scales. Right? The main scale, where does the 50th one is coinciding? This is 2 centimeters. 2.1, 2.2, 2.3, 2.4. This is 2.45. Right. So 50 scales of vernier aligned with 2.45 centimeter. So let's say one vernier equals 2.45 divided by 50. How much is that? If you multiply by 2 up and down, 100, 4.9. That means 0.049 centimeter is one vernier. One vernier scale is 0.049 centimeter. And in the main scale, what is the measurement you have in main scale? 0.05. See, this is 1. So this is 0.1. Half of that means 0.05. So each main scale, subscale is 0.05 centimeter. The difference between that and this has to be the minimum measurement. We studied that in measuring instruments. So let's say minimum measurement. 0.05 minus 0.049 centimeter, which is 0.001 centimeter. So the minimum reading you can get here is 0.001 centimeter. They asked us to give it in centimeters itself, right? In centimeters. Next. What is the adjustment that you perform on the eyepiece before starting the experiment? Simple. You have to make sure that you see the crosswire clearly, right? So adjust or calibrate it or adjust it to see the crosswire clearly. Right. Next. Now you are asked to place the given piece of paper on stage G of the travelling microscope and obtain the first measurement with the microscope using the mark X before placing the glass block. Write down the main steps in the experimental procedure you would follow to achieve this. So what do we do? Focus the microscope on X using the two knobs, right? What are the two knobs you are going to use? What are the two knobs you are going to use? Vertically large scale movement knob and fine tuning, vertically fine tuning knob. Let's use the names in the diagram. Let's go and see the names for them. It's easy. The names are A is for fine tuning, H is for large scale, right? So we can say focus on the cross vertically using A and H, using screws A and H. Simple. Focus the microscope on X on the cross using screws A and H, or will you write in the other order? We'll say H and A, because first you adjust with H, you loosen the H, move it and find out where, you can see an image, may not be very clear, but at least a blurred image you can see, fix it there. That is what you do with H, vertical large scale movement knob. Then what you do? Use the fine tuning knob and find where exactly the image is. So focus the microscope on X using screws H and A. Once clear image of the cross is seen on the cross wires, get the vertical scales reading. Mention that. Vertical scale reading. Remember, there are two scales in a travelling microscope. So you have to mention the reading I take is from the vertical scale, not on the horizontal scale. Next. Relevant positions of the main scale and vernier scale corresponding to the measurements mentioned in E above are shown below. Write down the reading corresponding to the measurement in centimeters. Right. See, first we will see where the 0 is. 4, 4.1, 4.2, 4.3, 4.4, 4.5, 4.6, 4.65 it has crossed. That's what you have to see. What is the last main scale that 0 of vernier has crossed? So 4.65 it has crossed. They are asking in centimeters, right? So this is in centimeters. 4.65 plus. Then we have to see which line of the vernier scale is coinciding with another line on the main scale. They have given the zoomed image of that. You can see here, I can say 42 is aligned. Can you see 42? And I told you earlier also, when 42 is aligning, the other two adjoining vernier scales will be inside the main scales. That means, if I further enlarge this and show, okay, this is where 42 is. Then this is where the main is. This is main. This is where vernier. Can you see? The other two vernier scales have to be inside the main scales. So main scales next one is here, vernier is before that. Similarly, main scales previous one is here, main scale is inside that. Only at one position, only at one point you will see this, not at anywhere else. Right, so that's how we confirm whether we have got the right one, because otherwise it might be a little bit confusing. 2-3 lines will look like they are aligned. So how do we confirm which one is aligned? Okay, if this is aligned, check the adjoining two vernier scales. They must be inside the two main scales. So in this case, we have 42 like that. 42 means that is each is 0.01, right? So 42 means each is 0.001. So 42 means 0.042. Correct. 42 into, we already found the minimum value, it's 0.001. That means this has to be 0.042. Add that with the main reading for 4.65 plus 0.042, what we get is 4.692 centimeter. 4.692 centimeters would be the reading. Correct? Vernier reading, you all are familiar with that. After taking the first measurement mentioned in E above, write down the important steps in experimental procedures pertaining to the other two measurements that you need to perform. Now what do? You just kept the paper and found the reading, right? Then what's the next step? Keep the glass block on top of that. Again focus and find the reading. On top of the glass block, you put some lycopodium powder. Focus on that and get the reading. Those are the two. So we'll write that. Place the glass block on the paper. We can add one more thing. When you're keeping the glass block, you can say with the vertical, with its lengthy sides vertical, right? Paper with its lengthy sides, with its length vertical. Focus the microscope on the cross and get the reading. That is a second reading you get. Then spread some lycopodium powder as a thin layer on top of glass block. Focus the microscope on the powder and get the reading. We have done this. This is the experiment we have done. So not that difficult for you to write it. It's very simple. Those are the next two steps you have to write. Reading of the relevant three measurements obtained by another student when performing this experiment are given below. So this is like R1, R2, R3. What is R1? Just to understand. See, the glass block. You kept the cross here. For this you got R1. Then the image of that was here. For that you got R2. Then you put the lycopodium powder here. For that you got R3. Right. Using these measurements, calculate the refractive index of glass. So refractive index N equals real depth divided by apparent depth. Real depth has to be R3 minus R1, right? This is the real depth. R3 minus R1 over apparent depth means R3 minus R2. This is the apparent depth. R3 minus R2. Straight away, can we give the answers? R3 minus R1 means I have to subtract these two. 7.206, 4.606. If you subtract it, right, you will get 2.6, isn't it? 2.600. R3 minus R2. Subtracting these two, you get 1.710, correct? 660, 10, 9, 1, 12, and this will be 11 and 4, that is 7. Then you have 651, 1.710. Let's divide this and see how much we are getting. 2.6, that is 26. Or let's say 260 divided by 171. 171, 89.5. That will be 850. Usually we give this in 2 decimals. So let's get another decimal. 850, 40, 400. 400 we'll get 2. Yeah. So 1.52 is the answer we are getting. Refractive index of 1.52. Understand? So once you have actually understood the concept of the practical, and then if you have gone through step by step how we have done this experiment, either you have to have the experience of doing it, if not you have to go through this, what we have done, what steps I have gone through to do this experiment. You had at least watch it twice or thrice. If you have gone through all that, then answering questions like this is not that difficult. Understanding the concept only, not having the experience of doing the experiment or not having gone through the experiment steps that I have done, then you will not be able to answer these questions. You saw that they're asking critical questions. They ask why the horizontal fine-tuning knob is not working. So unless otherwise, I explained this earlier. So unless otherwise you have gone through somebody doing the experiment like I did, you will not be able to answer those questions. So make sure you go through these videos at least twice or thrice and then attempt answering the questions. Right? So hope you have understood this experiment and the questions pertaining to that. Now practice all this. We will meet up with another experiment again.